Section 8.3 deals with compound interest. This is when you earn interest on your interest. This is great if you're talking about a savings account, not as good if you're talking about borrowing money, such as with a credit card. Let's take the example of saving $1,000 at a rate of 5%, compounded once a year. We're going to use the formula that we used before, A equals P times 1 plus RT. In year 1, we started with $1,000. At the end of the year, we have that $1,000 multiplied by 1 plus 0.05, our interest rate, times the time, which is 1 year. That works out to be $1,050. And that's what we have at the beginning of year 2. If we look at the second year, this time we start with a little more money. We start with $1,050. And we're going to multiply it again by 1 plus 0.05 times 1, because we're just looking at what happens between year 2 and year 3. At the end of year 2, or the beginning of year 3, that means we have $1,102.50. We would keep going with this, except we can actually model what's going on in this compounding with a new formula. And that would be A equals P times 1 plus R, and now instead of the R multiplying the T, we raise that whole thing to the T power. Again, A is going to be the present value, P is our principal, R is the rate, and T is the time. Now you might notice that this is not on your formula sheet, and there's a reason for that. This is only if we are compounding yearly. I don't want you to memorize a special formula just for compounding yearly. It was just easier to explain what's going on in that case. So let's look at what our general formula is. Our general formula is A equals P times 1 plus R over N to the NT power. A is, as before, it's the future value. P is also our principal, what we started this whole process with. R is the rate. Again, we're going to use this in decimal form. T is again time in years. And our only new bit here is N. N is going to be the number of times per year that interest is compounded. So in our case of compounding yearly, N is going to be equal to 1. And that's because we only compound interest once a year. If we look at the formula, if N is equal to 1, we find we get the formula that we got at the beginning of the lecture. However, again, I'm just as happy to learn one formula that we can use for all cases instead of memorizing a special case situation. If interest is compounded quarterly, that means 4 times a year, or N is equal to 4. If compounding happens monthly, then N is equal to 12. N is equal to 52 if we're compounding weekly, and again we'll use N is equal to 360 if we're compounding daily. Again, we're going to use this formula if we're compounding at certain times. If we're using simple interest, we'll use that formula that we used in section 8.2. Again, the toughest part of this chapter is understanding which formulas to use when. There's one other type of compounding that has a different equation, and that's this one. A is equal to P times e to the RT power. That's if we're compounding continuously, that is all the time, an infinite number of times per year. E doesn't stand for a variable. This is an irrational number, sort of like pi, that's on your calculator. And I'll go through a couple of examples to show you how to do this using your calculator as well as how to set up the problem. Say I have $2,000 to deposit in a savings account. It's going to earn 6% interest, and I want to know how much I have after 3 years. And let's look at different compounding periods. Let's go ahead and write the equation that we're going to be using for at least the first 3 situations. For all of these, A is what we're trying to find. That's the future value. The principal is how much I started with, which is 2,000. The rate is 0.06, and the time is 3 years. If I'm doing compounding yearly, N is equal to 1. Monthly, N is equal to 12, and daily, N is equal to 360. Let's go ahead and set up our equations. Here's our 3 equations. Let's first look at what happens yearly. And I'm going to go ahead and bring my calculator up. We're going to start with the inside parentheses, 1 plus 0.06 divided by 1, and I'm going to hit enter. That gives me what's inside that parentheses. Now I'm going to raise it to the 1 times 3 power. Notice how I put the 1 times 3 in the parentheses. If I don't do that, then the answer would just be raised to the first power instead of the 1 times 3 power. Finally, I multiply this by 2,000, and I get that I'll have $2,382.03 after 3 years. Now let's look at what happens when I compound monthly. Again, I'm going to start in the parentheses. I'm going to raise it to the 12 times 3 power, again being careful about parentheses. And then I'll multiply this by 2,000. This time I earn $2,393.36. So I've made a little more than $10 more by compounding monthly. Now let's look at the same question, but compounded daily. Again, I'll do the bit in the parentheses first, then take care of the exponent, then multiply by 2,000. This time, it looks like I only made about $1 more. The difference between monthly and daily wasn't that significant. Next, if they talk about continuous compounding, I need to use a different formula. I'm going to use A equals P e to the RT. Since they didn't tell me how often I'm compounding, I wouldn't be able to find N. So if you get on in the exam and you think, gosh, I don't know what N is, that's a hint that you need to use a different formula. If I plug in P, R, and T, this is my formula, and let's go ahead and plug this in the calculator. I'm going to go ahead and type 2,000 times, and E is found by pressing the second button and then the LN button. And that gives me e to the, what I want to raise that e to is 0.05 times 3. And when I do that, I find that if I compound continuously, that's odd. I get an amount less than compounding daily. This is the type of problem that you can run across on an exam. You look at this and think, gosh, this can't be right because compounding all the time should be better than compounding just once a day. What I would do is write down your answer and write, gosh, this doesn't seem right, but I can't find my mistake. And then as I'm grading your exam, I'll say, oh, I see your mistake. You forgot that we were dealing with 6% interest, not 5% interest. So if instead of 5%, I correctly used 6%, then we get an answer that's more reasonable. It is higher than the daily amount, but only by 3 cents. But it doesn't make sense that it could have possibly been smaller than the daily amount. Let me go ahead and fix this for the notes. Alright, that's an example of finding out the future value. But we could also solve the same kind of problem that we did before, which was to find out how much do I need to save to get a particular future value. Let's go ahead and do that. Say I need $20,000 in 5 years. I have a savings account that will earn 6% interest compounded monthly. And I want to know how much do I need to save today in order to have $20,000 in 5 years. A is my future value of $20,000. My time is 5 years. My rate is 0.06, and my N is 12 since I'm compounding monthly. Let's go ahead and fill out the equation. Let's go ahead and put this into our calculator doing the parentheses first. Now I'm going to raise what's inside the parentheses to the 12 times 5 power, again using my parentheses, and then I get a number. I'm not going to write all the numbers down on my paper, but I'm going to leave it in my calculator so that way I keep the most amount of accuracy as possible. I'm just going to say 20,000 divided by second answer, and that uses the 1.348850153 that I just got as an answer. And I get $14,827.44. And that's how much money I would have to save today in order to have $20,000 in 5 years in a savings account that earns 6% interest compounded monthly. Lastly, we're going to calculate effective yield. Effective yield doesn't take into account principal. What it does is take into account the rate that you get plus the compounding. So if you had a 5% interest rate compounded daily versus a 5.1% interest rate compounded yearly, in fact, anytime you go online and if you're looking at borrowing or savings rates, these rates are always given in terms of effective yield. That is, the government has said banks need to talk about the effective yield which takes into account compounding. Let's do an example. If I have a 5% interest rate that's compounded daily, the actual yield is going to be this. Let's go ahead and find this on our calculator. Again, inside parentheses first, then I'm going to raise it to the 360 power, and then I'm going to subtract 1 from it. So a 5% interest rate daily compounded actually gives me a real interest rate of 5.13%. This is also called annual percentage rate. So on those commercials for car loans, you'll hear about APR. So that is compounded, worked into the the actual interest rate.